So when the paper came out, then it seemed that I was the only person in the group who had sort of the knowledge of what was required. And so they asked me to give a series of talks. So I thought it was for students and postdocs that I can explain what the general ideas are, what Hawking is saying, and so on. And to my shock, the first day, there was Chandra in the audience.
Chandra is a towering figure in the University of Chicago, and just going and approaching, meeting him first time would have been, special thing for you. Also, later on, every time meeting him on the premises and having interaction. So, tell us about your interactions with
Professor
Professor.
Chandra. As I mentioned just 2 minutes ago, right? I mean, about Chandra's style of working. He was not like Bob Geroch. He was not bubbling. He was much more calm and much more precise, much more sharp. Bob Geroch, had never tucked in his shirt. His shirt was always out. Chandra came in a three-piece suit, which there were woolen suits in winter and silk suits in summer. So very different personalities. But when it came to science, they were equals, right? I mean, Chandra, as I said, Chandra invited these three young.
He's learning from.
Yeah, exactly. Three young, people in their mid-20s and took notes and called them. So Chandra had this attitude about knowledge and science, which was unbelievable. And so, so it turned out that the interaction, as you say, when I first went, Chandra was like a god for me, right? I heard so much about Chandra and from everything, right? From his episode with Eddington and things that he'd done on the boat from going from India to Cambridge, and I heard all these stories, and so he's really not a human. He's like a god or something like that. And then seeing him in seminars, interacting, treating us as if we were his equal. Was the way that we felt more at ease. It's not that he was, tolerated, stupidities. There was a younger student who would put his feet on the chair, and Chandra would tell him to sit straight. It's not so he was. It's not that he did not have his standards, or he did not use his standards to the students. But when it came to intellectual query, he was just completely one of us. So, of course, it was very slow that my interaction with him grew, right? The first year, it was not so much. My first year in Chicago, so my third year in graduate student. But my fourth and fifth year, there was a really close interaction. The times, particularly in the last year, he would actually call me to his office, and, we'll discuss some science. But then he would also air things, general things. And particularly the last year. And so at that stage, he was 62 at that time. No, 63 maybe. And so he would, he always read up a lot, right, about what other great men or women did in their life and their biographies. And he knew a lot of first-hand details, and also because he was a fellow of the Royal Society, he had access to the personal memoirs. And so he was telling about Rutherford. And so, he would pull up these anecdotes from all the historical figures, right? That I'd only heard of. So with Lord Rutherford, he used to say he wondered if, in fact, a man after 60, because in those days, scientists were all men, right? So there's a man after 60, does he do more harm or good to science? So, and Chandra was 63, right? So he had obviously thought quite a bit about this question. And he said that, well, then Rutherford replied, he says himself, I think Rutherford had raised this question to his son, and in that discussion, this came up. And Rutherford replied, his son was also a physicist, very famous. So he said that he came to the conclusion that if the person does not get in the way of younger people, then there's no harm in continuing. And they may even contribute or something. So he had thought about such thing, and these are kind of, in some ways, in retrospect, very intimate thoughts, right? Because one is 60 and one is talking about, are you useless? Are you doing more harm, or are you doing more good or something? So there were such things that were very, very, very nice of him, that Chandra. By the way, when I did reach 60, I didn't forget this, and I kept that in mind, that what one should do and what one should not do and such things. And in fact, last week there was somebody's 60th birthday, and This conference was in their honor, and so I again went and told them this story of Chandra. So it's a good thing to remember. But also otherwise, right? I mean, because the group was small and nice and everything, and particularly Bob Geroch's free spirit, niceness personality. It's not egoless personality. That I think. So we used to once in twice a year or something, we would have a potluck dinner. Right now, so they would rent some space and we would bring everybody would bring some food and we would share food and eat and so. And then at that time, then people said some things, and so Chandra would tell us stories about Geroch and about everything. So that's a personality which is very very nice. I mean, it's yeah. Also personally, he told me about these stories about Geroch, about how he and Geroch would go for long walks on Sundays. Geroch liked to take a long walk on Sundays, but they were completely quiet because Geroch didn't speak very much. Geroch was very well known for that, not speaking. So we heard a lot of interesting stories from Chandra.
During your time at Chicago, right? At that time, Hawking discovered, I mean, he wrote a paper about Hawking radiation. And from my reading, I gather that you had to present that to Professor Chandra and a large audience. So could you tell us about
Yeah, right.
that?
Thank you. Yeah. So this was I think in 1974. So this is when I finished this summer, or I went to Oxford in September. So I finished sometime in August or July of 1974. But that spring, in those days there was no internet, so we all got preprints, right? So no, I didn't get it. I mean, the professors got preprints. So Bob Geroch had this preprint. Bob knew Stephen Hawking quite well because he was a postdoc in Oxford, and they're roughly the same age. Stephen was also a postdoc at that time, and they in fact proved some theorems which are very similar to each other, so-called singularity theorems. The most famous are the ones due to Penrose and Hawking, but also the Geroch, so the singularity theorems. So this Geroch had these preprints, and so and it was considered to be a famous thing. So let me say what it is to put it in perspective. So basically, it had to do with black holes. Chandra's work basically showed that the collapse could be halted if the mass of the star is not too high, because as the star collapses, basically you just have either electrons or neutrons. For our purpose, it will be neutrons. There'll be inverse beta decay in which the protons absorb electron and the neutrino and become neutrons. So, but then neutrons are spin 1/2 particles, so you cannot put two of them in the same space, same place, and therefore there is an effective pressure, outward pressure. And so if then the star is collapsing, this effective outward pressure can balance the gravitational attraction. But gravitational attraction increases with the mass of the star, whereas this effective pressure that we have talked about doesn't increase with the mass of the star. So if the star is very massive, then this equilibrium would not occur, and one would have a black hole, basically. Chandra was talking about white dwarfs, not neutron stars. I'm talking about neutron stars. But exactly the same idea is applicable to neutron stars. So people didn't believe in black holes. Most astronomers did not believe in black holes. There are exceptions, but most astronomers didn't believe in black holes. And there's just figment of imagination, Einstein relativity, etc. It's all not relevant. But then, in fact, it is really true, because Chandra was working on black holes, for example. His masterpiece is on mathematical theory of black holes. But his students, when they gave a talk in MIT, is a leading place in this talk, right? The leading physicists there say, yeah, this is all fine that you're working on this, but these are all mathematical ideas. They have no physical relevance. Why are you spending so much time? I mean, and this was I'm talking about mid 70s now. And Chandra had done the work in the 30s, right? Early 30s. So there was a reluctance to accept that there can be black holes in the world. And now the astronomers are completely flipped over. Now they think there are black holes everywhere, right? I mean, it's a completely interesting transition. In the early 70s, thanks largely due to Stephen Hawking, but he took some seminal ideas of Roger Penrose to develop this theory of black holes and so on. And then there was a precise formulation of black holes, because previous discussions were all tied to simplest solutions of Einstein's equation, Schwarzschild solution of Einstein's equation. So Stephen Hawking and Brandon Carter, that I mentioned, that Chandra had invited to lecture him together with Bob Geroch and George Ellipse. So Brandon Carter and Stephen Hawking, they had developed these theories of black hole much more. And classically, black holes are completely black. But then Jacob Jacob Bekenstein, who was also a student of John Wheeler's, just like Bob Geroch was a student of John Wheeler's, in his PhD thesis, developed a lot of thought experiments. Because he said, well, supposing I got a boiling cup of tea here, okay, and here is a black hole, and I go and so it has a lot of entropy, and I pour it into the black hole, and so the tea disappears, the entropy is lost, so I can violate the second law of thermodynamics by reducing the entropy in this particular way. And so it looks very weird. So therefore, they thought that no, if I pour the tea in the black hole, then the black hole's entropy should go up. But what is black hole entropy? How can it have entropy? Because it is completely black. That is to say, if something is completely black, it has zero temperature, and at zero temperature, object would not have any entropy. So how can it be, etc. So Bekenstein came to the conclusion that you can associate a multiple of the area as the entropy. Now, the entropy is dimensionless because the logarithm of number of states, whereas area has dimensions of length squared. So that means that you need a constant. And Bekenstein said that so-called Planck length, which is to say bring in h bar, would be that constant. And so his point was that if h bar goes to zero, then entropy becomes infinite. So black hole has infinite entropy, if you like. But if h bar is, in the real world, h bar, the Planck's constant, is finite, and then that would make the entropy of the black hole finite. So he suggested this idea, but still, it seems strange. It's a completely black object. It has zero temperature. How can it be? And even Hawking initially thought that no, these laws of black hole mechanics, as they are called, these are all just analogies with thermodynamics. They look like thermodynamics, but you should not think of in thermodynamic terms. Area is area, so-called surface gravity, etc. But Bekenstein suggested that area is related to entropy and surface gravity is related to temperature of the black hole. But then people thought it was wrong because temperature is zero, surface gravity is not zero, so how can it be right? So the Hawking then did the following calculation. He said that supposing I got a black hole geometry and I just have a quantum field in it. So the matter field is quantum mechanical, geometry is still classical, and the quantum field starts out in the vacuum state. So that is, there's nothing, there's no excitation, there's no energy in the black. But still, because the black hole has a gravitational field, it can pump energy. Energy can be transferred from the black hole into the quantum field. And then Hawking did this calculation to show that, in fact, because that such a process exists and the black holes can actually radiate as though they were black bodies at some temperature, and that temperature was then the same as the h bar times the surface gravity, and as h bar goes to zero, it does go to zero. So in classical general relativity, the temperature is zero, entropy is infinite. But when you bring in h bar, when you bring in quantum effects, then the statement is different. That is, so it was a big shock in the physics community about this. Of course, outside gravity, people didn't take it seriously. Even much later, people didn't take it much seriously. But it has some rather startling consequences the way that Hawking first proposed it. Hawking withdrew much later in his life. He withdrew. We'll talk about that when you talk about quantum gravity and such things. But I mean, Hawking effect is real. But then what he built on it, and he came to some conclusions which he withdrew later on. This basic idea that black holes radiate quantum mechanically was a new idea. And since I had been thinking about quantum gravity, and actually I had even written a paper with Bob Geroch on quantum gravity. So when the paper came out, then it seemed that I was the only person in the group who had sort of the knowledge of what was required. And so they asked me to give a series of talks, 2 or 3 talks, not nothing. So I thought it was, mainly for students and postdocs that I can explain what the general ideas are, what Hawking is saying, and so on. And to my shock, the first day, there was Chandra in the audience, which I didn't. He came to all the talks, and also there was a famous particle physicist, high energy theorist by name Aichiro Nambu, who then later on got Nobel Prize as well. Yeah, he has very influential ideas in particle physics. He was also in the audience, and they were asking questions about the Hawking effect, and it was very nice to say a few things about it. I mean, in part, this happened because of this review paper that I told you about with Bob Geroch on quantum gravity. So
Yeah.
normally review papers are written by senior scientists who have worked in the field for a long time.
To summarize the state of the
State of
field.
the field. So when I started working with Bob, I wanted to do quantum gravity. At that time, I was reasonably ambitious. And so Bob felt fine. He had not worked in quantum gravity, he had worked on classical relativity. And after me, he did not really do quantum things either. I mean, while I was there, he did write this lecture notes on geometrical quantum mechanics, which actually a lot of it was also discussions between us, but it was really Bob's lecture. I mean, I profited much more than he profited from me. But then we decided we wanted to understand the subject, and typically Bob likes to understand the subject in his own way.
Okay.
And so instead of just reading the literature and reproducing what it is, we tried to project our understanding on the literature. It's opposite of what normally does. Saying, well, I mean, these are the basic ideas of relativity, these are the basic ideas of quantum mechanics. If you combine them, then these are the possible things that can happen. Oh, this particular approach puts quantum mechanics on forefront and relativity as a backdrop, and then this comes out. This approach puts general relativity on forefront and quantum mechanics adds on to that later, and then this happens. We'll talk about this more
Okay.
when you talk about quantum gravity. But so we wrote this first paper. So my first paper is actually exactly 50 years ago now. 1974 it appeared, and it was on quantum gravity. And when this paper was written, the funny thing is, there's also a funny story about it that Chandra told me, since you are asking me about Chandra. So we first wrote this paper, and then we wanted to submit it somewhere. And we thought, that Bob Geroch had some American journal in mind, a very good journal in mind. But apparently Chandra persuaded him to submit it to a British journal, which Chandra was aware of. So, which is called Reports on Progress of Physics. And so Bob was a senior author, so he sent the paper to them. Although, my name comes first because of its alphabetical order. And I should say that, I mean, a lot of writing was Bob's because he had this beautiful way of writing. I learned a lot from that. But then this article went, and then we got a letter back from the editor, who was some senior physicist, basically saying that, well, they had just published another article a year or two ago on the same topic, so they don't want to publish it or something. So Chandra told me later that, therefore, Bob Geroch went to him and said, well, I mean, we sent it to the journal because you suggested, and this is the letter we got. So apparently Chandra wrote to the editor and probably saying extremely complimentary things about us and about the article. So then the editor wrote back saying, actually, on second thoughts, we will publish your article. So it actually got published. So I know this only from Chandra. I've not seen any documents about this thing. So this was an interesting episode. But for example, in writing this article, again, something comes up about personalities. At one stage, we sort of had gathered ideas about various approaches, and quite a bit of it is actually very heavily influenced by these ideas I brought from this course in mathematics that I took in Austin. I mean, of course, we developed it further or something, but we applied it very nicely there. And it's a new way of looking at many things. Dirac had developed a theory for general relativity. It's called Dirac theory of constraints, because it is the dynamics is constrained in a very non-trivial way, and what happens, and it was all in coordinates, and it was of course completely right, but its real meaning was not clear to us. And so we, Bob mainly, put it in a more geometrical language in which the invariant content of it was completely clear. If you like, invariant content means that you leave all the extra baggage out, and you only keep the things that are essential to make the arguments. So we had done this in classical relativity, and then for quantum theory, we use these ideas from algebraic quantum field theory and so on and so forth. And so that was a quite useful thing. So, I mean, just as to close then, I just want to say that in my Chicago experience, really, Bob Geroch and Chandra were my mentors. And I learned enormous amount of things from them. Right? Absolutely. I mean, many years later, I wrote to Bob saying that, well, I really often feel that everything I know came from you. I mean, it's outgrowth of what Bob taught. I developed it further, but in some ways, Bob's greatest strengths is incredible clarity and penetrating reasoning, right? So basically, as I said about this paper, we did not just read the other papers and report what they were doing. We first had a viewpoint, and we looked at how these various papers fit in that particular viewpoint, right? I mean, and so we had developed a kind of a framework to think in terms of which to think about quantum gravity.
Yeah.
So Bob was like that. He liked to develop his own framework, and he continued to do that. And so I learned that from him. And so I just want to give you one simple example about this. That in those days there was no internet, so one had this Bob Geroch and Chandra would get these preprints, right? Bob Geroch would get more mathematical relativity preprints, Chandra more astrophysical ones. So, but very often, once a week, we went to a pizza place with Bob. And Bob would bring a bunch of preprints. And we were supposed to read the title and the abstract.
Okay.
And then guess how this was proved.
Without
Instead of reading the paper, you are supposed to think about it yourself in your own way or something. So this is the style that I picked up with Bob very, very much, namely even today, right? I mean, it's much easier for me to, I listen to an idea in a talk. It's much easier for me to try to work out that idea than to go to the paper and read the paper, so to say. I mean, what this does is to give you a perspective which is kind of your own, in which everything is unified, right? I can be doing black holes, I can be doing Big Bang, I can be doing some mathematical theory of general relativity, I can be doing some pure mathematics problem, so-called symplectic geometry, problem in geometry, but it will be a unified viewpoint. I can make connections between these two things because they all come. It's not that I just learned this from here, this from here, this from here, this from here. They're all folded into my understanding. So that's a great strength of it. And that is what I learned from Bob Geroch. And I think on the whole, I'm very happy with it. But it does have severe limitation. And as I perhaps mentioned to you, when I got much older, I realized that one's greatest strengths are one's greatest limitations also. They're the other side of the coin. Because people who can quickly read a paper and see, they proceed much more fast than I can do because I have to redo the paper in my way. It takes much longer. And so I sacrifice speed in favor of unity and a unified picture and a solid core, if you like. And people who learn a little bit here, 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 in that they all make a connection between this and this, two extremes. But in the one area that they are looking at, they're much faster than I am. And so therefore there's this other side of the coin that I came to realize, also much later. From Chandra, what I learned is not so much technical things. I mean, it's not that I did not learn technical things, but not so much. But I learned much more what it is to be a scientist. What is the core of a scientist, right? I mean, he would he would tell us his stories, and he would tell me his own role, tell me other people and such. And of course, he never criticized other people, but from the way he said it and such thing, one could see what he valued and what he thought was lacking in some other people and such thing. And so that, I think, shaped my attitude towards science very, very much. And so these are the two things. And the third thing that came is from my postdoc years from Roger Penrose. So basically, Roger Penrose and Chandrasekhar and Bob Geroch are my mentors in the anti-chronological order. And I learned very different things from the three of them. And I think that all of them I value enormously. And I'm most grateful to them and also to the fortune or whatever it is that I got to interact with them. Okay.
It's very interesting to walk down the history lane and learn a lot from your experiences. I'm quite sure that this is going to be really helpful to all the researchers and students. So thank you so much again spending time with us.